Welcome to Support Vector Machines Part 3, and let's go ahead and get started. Okay, so remember, we had a data set, right, with two classes in it, class 1 and class 0, right? And class 1 is being represented by an X, so each data point here that's has an X is a example of class 1, and class 0 is represented by a circle, so every data point here that's a circle is a example of class 0. Right, and we developed our goal was to separate these two classes in the feature space using the features x1 and x2, and we create a model, a linear model, W transpose times x of I plus b is equal to 0, right? That separated these two classes. You see it separates the x class, or class 1, from class 0, or the circle class, right? And remember, the way we classify these examples into class 1 or class 0 was we looked at if W transpose x of I plus b is greater than 0 or less than 0. So if you're on the side, this side of the line, then maybe W transpose x of I plus b is greater than 0, so you're classified as class 1. Right, and if you're on the other side of the line, so to the left of the line, then you'll be classified as class 0. Right, and I think that's a good enough review for right now, and so let's move on. Alright, so I want to remind you of the rule for classification again. So remember, if W transpose x of I plus b is greater than 0, then the example will get classified as class 1. And if W transpose x of I plus b is less than 0, then the example will get classified as class 0, right? Where x of I is the example that we're trying to classify. Now let me explain that in terms of these graphs and W. Right, so let's say... right, remember, W is a vector that's perpendicular to the line W transpose x of I plus b is equal to 0. Right, so W would be a vector in this direction. Right, and the same for this line too, because these are the same model, just drawn twice. Right, and any data point, right, in the feature space, any x of I example, right, is basically just a point in this feature space. And so if I mark a new point in the feature space, right, and I ask you, what class is this example? Well, you would see if W transpose x of I plus b is greater than 0, right? And so what you can do is, if you draw the vector to that example, right, you can see that the vector W and the vector x of I here, right, this vector x of I, the dot product between those two would be positive, so it would be greater than 0, so it would be classified as class 1, right? And in the opposite case, if your new data point somehow fell here, right, and so this is your x of I, right, your new example, and it has a vector, right, you can represent it as a vector here, you can see that the dot product between W transpose and x of I is less than 0, right? So that it gets classified as class 0. And that's how the rule for classification works. Alright, so now let's move on from that. Alright, so we want to avoid misclassifications for our model. Remember, our model is W transpose x of I plus b is equal to 0. And this model, remember, it classifies new data points in the data set via this rule we described here, right? And so when we make a misclassification, we could either classify a X example, the true class of the example, as a 0 or as a circle example, or we can classify a circle, which is the true value of the example, as the X. Right? These are the two different ways you can make a misclassification. Right here, I demonstrate that with these two red points. Right? Because this circle here, right, would have a positive dot product with W, right? It would get classified as a X, but that's the wrong classification because it's really a circle, right? And same thing for this X, right? Because the dot product between this X and W would be negative, right? This X would get classified as a class 0, right? Classified as a class 0 or a class circle. And so it would be a misclassification because its true class is X, right? And each misclassification should have a cost, and this is how we're going to build up a cost function for this model so that we can optimize it so that the model can be as good as possible or fit the data set as close as possible. And so let's move on from that. All right, so before we move on to how we detect misclassifications and how they're going to make a cost function, we actually need to make some adjustment to the data set. So remember, y of I was a vector that described the class of each example in our data set. So for this specific example here, right, the first example will be class 1, second example will be class 0, third example will be class 1, and the int example would be class 0, right? What we need to do is we need to change the y of I value for class 1 and class 0 to be where class 1 has a y of I still equal to positive 1, but class 0 has a y of I equal to negative 1. So that this vector would change to example 1 being part of class 1, and example 2 having a negative 1 value for its y of I that tells us that it's part of class 0, right? And then the third example and fourth example as well. And so this is just the adjustment we need to make because it's going to be important later when it comes to actually computing a cost function. And let's move on. All right, so there's actually two ways of misclassifying. There's only two ways because we only have two classes here, class X and class O, or class 1 and class 0. All right, so there's only two ways of misclassifying. Either we can have a false class 0, right, where y of I is equal to negative 1, so the example is part of class 0, but our W transpose X of I plus B for the example X of I is greater than 0, so we classify it as a 1. Right, so we classify it as a part of class 1, but it's actually part of class 0. Right, and then we have false class 1, where the example is actually part of class 1, so its y of I is plus 1, but our W transpose X of I for the example plus B is less than 0, so we classify it as class 0, but when it's actually a class 1. Right, so there's only two ways of misclassifying. Now, if you notice, right, if you think about what y of I is and the kind of sign of W transpose X of I plus B, you'll notice that y of I times W transpose X of I plus B is always less than 0 for a misclassification. Right? Because here y of I is negative 1, and W transpose X of I plus B is some number greater than 0, so negative 1 times some number greater than 0 is a negative number, right? And then same thing here, positive 1 times some number less than 0. Well, that's just going to be a negative number times positive 1, which is just going to be a negative number. So y of I times w transpose x of I plus b is always less than 0 for a misclassification. And so we can use this to actually detect if any given example is misclassified in our data set up here, right? So this x here, right, would have a misclassification and would have a negative product of y of I times w transpose x of I plus b, and so would this O point, right? But all these other black x points and these black O points would have a positive y of I times w transpose x of I plus b. Now it's actually more useful to use negative y of I times w transpose x of I plus b. The negative of this is always greater than 0 for misclassification. Right, always greater than 0 because we want our cost to always be positive. Right? And so now that we understand that for misclassified data points, right, this product y of I times w transpose x of I plus b is always going to be less than 0, and so the negative that's always going to be greater than 0, we can actually start to construct our cost function. And let's move on. All right, so now we know that negative y of I times w transpose x of I plus b, right, is always greater than 0 for misclassified examples in our data set, right, an example x of I comma y of I. We can construct a cost of a single example, right? So the cost of a single example x of I comma y of I is going to be equal to the max of between the two values 0 and comma negative y of I times w transpose x of I plus b. Right, now let's spend some time on this cost function, right? So remember this value here is always greater than 0 for a misclassification, right? So if this value is always greater than 0, right, then between 0 and this value, right, this is always going to be the max of it, right? It's always going to be greater than 0 if we have a misclassification. So this is always going to be some positive number if we have a misclassification. Now, if we have a proper classification, remember y of I, negative y of I times w transpose x of I plus b, right? This value now would be less than 0. So in that case, the max would actually be, right? Not in that case, when we actually have a proper classification, we have a proper classification. So we classify a class 1 example as class 1 or a class 0 example as class 0, right? Then this product, this value is always less than 0. So the max of between that and 0, between a value that's less than 0 and 0 would be 0. So for proper classifications, this function always gives 0. So when we properly classify, we get 0 cost, and when we misclassify, we get a cost of y of I times w transpose x of I plus b, right? And this y of I times w transpose x of I plus b kind of tells us how badly we screwed up the classification, right? So here in this graph, I drew our model, right? Our w transpose x of I plus b is equal to 0 model, right? And here we have, and it separates the two classes, and here we have these two red points that are misclassifications, right? They're classified as class X when they should be classified as class 0 or a class circle, right? But this one right here isn't that badly misclassified, but this one right here is very badly classified. It's very far away from the circles, right? We're very far away from this boundary, the w transpose x of I plus b boundary. And so in this case, right, w transpose times x of I, right, w basically the dot product between w and x of I is going to be large, right, because this is very far away from the decision boundary, but this one is going to be very small because it's very small distance away from the decision boundary. So this one is going to have a lower cost, right? And this one's going to have a higher cost. And so this is why this function here is going to be our cost function for any given misclassified example. And let's move on. All right, so the cost function of our SVM model, right, W transpose xy plus b is equal to 0, right? We have the cost for a single example, x of I comma y of I, but we want the cost over all examples in our entire data set, right, where we have x1, x2, all the way to capital X in examples, right, in our data set. And so we want to minimize the cost across all examples in our data set. And so the true cost function, the true cost of our parameters w and b that form that are in our model is equal to the summation from I is equal to 1 to capital N, right, that's the number of examples, of the max of 0 comma negative y of I times w transpose xy plus b, right? So this basically computes the sum of all the costs for each example in our entire data set here, right? So in this one, we would only have these two examples give us any cost, and everything else would have 0 cost, right? So we want to minimize this cost function, right? And we want to minimize this cost function to get the best SVM, so the best W vector value and the best B constant value, right? And ideally we want this cost to equal 0, right? So we want basically every example to be properly classified so that the max of this, the max of 0 comma negative y of I times W transpose xy plus b is always 0 for every single example I equals 1 to capital N in our data set, right? So that's what we want to do. And so with that, let's move on. Now, let's say our data set is linearly separable. By that, I mean that the W transpose x of I plus b equals 0 line, right, that divides the two classes, can properly classify all examples x of I comma y of I, right? So here you see the model W transpose x of I plus b equals to 0, separating these two classes perfectly, no misclassifications. This means that our cost, right, would equal 0, right? So that's good, but there's going to be a problem, and the problem is that many models can satisfy this, right? Many different W and B values can satisfy this cost, right? The cost being 0, right? So there could be another W2B1 that also has a cost that's also 0, and it could be another W3B3 that has a cost that's equal to 0, right? Say like a line like this, right? A line like this, right? It still perfectly separates this class from this class, right? It makes no misclassifications, but it's different from the blue line. So we don't know there's a whole set of models that would satisfy this, the cost function being 0. And we're going to need to figure out a way to choose between them, right? How can you choose between this blue line and this red line? And with that, let's move on. Okay, so here I drew 3 models that satisfy the cost of the model being 0, right? For a cost function, the summation from I equals 1 to capital N of the max of 0, comma, negative y of I times w transpose xy plus b is equal to 0, right? I drew 3 models that satisfy this cost function equation, right? Model w1 comma b1, right, which is this light blue model, right, separates x class from the circle class perfectly. This blue model w2 comma b2, right, separates the 2 classes perfectly, and this third model w3 comma b3 also separates the 2 classes perfectly. Right, so these 3 sets of parameters all satisfy the cost function equal to 0. So how do we figure out how to choose from between these, right? All these are just as good, right? Not quite, right? W3 comma B3, right? This red model is actually better, and it's better because it leaves a large gap between the 2 classes, right? Here, right, for W2, B2, there's like a really small gap here, right? So if your data point shifts just a little bit upward, right, in this direction, then you would make a misclassification, right? And same thing for this blue line, right? If an X class shifts just a little bit to the right, right, you will make a misclassification. But for the red line, right, the X would have to shift quite a bit, and the circle would have to shift quite a bit to make a misclassification. So this red line is better. And this is related to what's called the margin, right? And later we're going to add what's called the margin to the cost function so that we can actually choose between which one of these is the best model. In this case, it would be W3, B3. But I will describe what the margin is in more detail in a later video, right? But our cost function will then look like the original cost function, right? Summation from I is equal to 1 to capital N of the max of these 2 values, but plus a new margin term, which has to do with this gap I explained here between the 2 classes. All right, so that's the end of this video. If you liked it, give it a thumbs up, and I'll see you next time.